All right, we're going to start back up. I used my whiteout. I like using the marker because you can see it, but I can't erase it, and I couldn't find my whiteout. This is 5 times 16, and 5 times 16 is actually 80. So rather than 5 pounds, my numerator is going to be 80 ounces, and we're going to divide that by 20 ounces, and the ounces cancel. And 20 goes into 80 4 times, 20 goes into 20 once. So we would say the ratio there is 4 to 1. How about E? Here we have 5 pounds to 2 feet. These are not commensurable, they're incommensurable. M-E-A-S-U-R-A-B-L-E. Why? Because pounds is a unit of weight and feet is a distance. So there's no way we would be able to cancel them. So that is not a ratio. And F, how about 4 meters to 30 centimeters? And there are 100 centimeters in a meter. So my new numerator is going to be 400 centimeters to 30 centimeters. And the centimeters are going to cancel, and I'm going to divide by 10, and so that rate, or that ratio, is going to be 40 to 3. So you can see how we simplify our ratios. And they wind up having same units in the numerator and denominator, so you can actually wind up canceling. And your ratio winds up being just a number. A rate is a quotient, which means numerator divided by denominator, that relates to quantities that are incommensurable. All right, so here, like a car, if it goes 30 miles on 10 gallons of gas, that would be like 30 miles to 10 gallons of gas. We can't eliminate or get miles and gallons to be in the same unit, but we can reduce. And so that would be 30 miles per 1 gallon, or for a unit gallon. And we would write that as 30 miles per gallon. That's considered a rate. A rate. A rate has different units in the numerator and in the denominator. So now a proportion is a statement that equates, meaning there's an equal sign, two ratios or two rates. So here I have A to B equals C to D. Another way I could write that is A to B equals C to D. And when you write it like that, you can see that in the middle here, we're going to call those the means. The means are in the middle. And here, the ones on the outside, we're calling those the extremes. So in our proportion, the A and the D are the extremes. They're the first of the first fraction and the last of the second fraction. The B and the C, these are your means. And when they're actually the same number, they are your geometric mean. So when you set up a proportion, you'll have two rates or two ratios equal to each other. And you can actually solve proportions. In geometry, we would say the product, which means multiply, of the means is always going to equal the product, meaning multiply, of the extremes. Now in algebra, you called this cross multiply. But this is not algebra class, this is geometry class. So we say the product of the means equals the product of the extremes. And that's what this property is saying right here. So a proportion will have an equal sign, and because its proportion is a statement, it's either true or it's false. So if you were to multiply, if we want to see if this is a true statement, is the product of the means. Does that equal the product of the extremes? Does 6 equal 6? Yes, that's a true statement. Here we had 9/12 equals 2/3. This is a proportion because we are equating two ratios, but is the product of the means, 2 times 12, does that equal the product of the extremes? Does 24 equal 27? It does not, so this is a false statement. So again, in algebra we would have said we cross multiplied, but in geometry we're going to say the product of the means equals the product of the extremes. Now I've already hinted to this, but if you have a proportion where you have the mean, the number in the mean spot is the same. If you have the same number in the denominator of the first fraction and the numerator in the second fraction, that is called the geometric mean. And we're going to find out that in some of our properties, like with triangles, certain proportions of a triangle are going to wind up being geometric means. So if I had 1/2 is equal to 2/4, we would say the geometric mean is 2, because it's in the means position and it's the same number. Now you can have an extended ratio that's going to compare more than two quantities. All right, so if we were comparing 3, it'd be A to B to C, or D to E to F to G. So for instance, if you know the angles of a triangle are 90 degrees, 60 degrees, and 30 degrees, you could write that as 90 to 60 to 30. And if you wanted to reduce that, the exact same extended ratio divide by 30, that would be 3 to 2 to 1. If there is an unknown quantity, let's say we have 4 values and they are related in a ratio, we're going to represent the unknown quantity to x. Give it the variable x. So if I had s is to t is to r, and I was told that that equaled something, like they all equaled, when you summed them up, 180 degrees, that would be s times x plus t times x plus r times x would be 180. So if there's an unknown quantity, you're just going to use your variable x, which we're used to doing. So when you set up these proportions, you have to make sure that you are consistent with what's represented in the numerator and what's represented in the denominator. There is not just one way to represent a proportion, but there are several ways you can mess it up, and you have to be very careful. So if I had, I'm given A to C as the same as B is to D. Another thing I can do here is I can swap numerator and denominator. I can put C in the numerator and D in the denominator, and they are equivalent. as long as C and D are both my denominators and C and D are both my numerators. If this was my original proportion, I can set the proportion up A to B as long as I go C to D. A to B is in the same proportion as C is to D. And you know what? I can swap numerator and denominator here too. I can put B in the numerator and I can put D in the denominator. So that's just saying that there are various ways to write the same proportion. One is not better than the other. They're all correct. The idea is you have to be consistent. If we have 2 to 3 equals 8 to 12, well, we were originally given 2 to 3 and 8 to 12. So I can swap the 2 and the 3 and the 8 and the 12. Just change numerator and denominator. I can go across 2 to 8, 3 to 12. That's that one. Or I can go swap numerator and denominator. Here I could have put 8 to 2 as 12 to 3. And here I can actually go back, rather than 3 to 12, I can do 12 to 3, 12 to 3 as 8 to 2. So as long as you're consistent with what's represented in the numerators and what's represented in the denominators, all of the proportions will still be correct, still be maintained, just as long as you're consistent. All right. And here's something that you can just memorize or get used to detecting. I can add the same term to the numerator as is in the denominator. I can add the same term as is in the numerator as is in the denominator to both sides of the equal sign. Or I can subtract. Why is this true? If I had A over B equaled C over D, let's say I added 1 to both sides. Well, you know you cannot add fractions unless they have the same denominator. So I'm going to rename this 1 as B over B. So it has the denominator I need on the left-hand side here. I can rename this 1 as D over D. So it has the same denominator. Now that they have the same denominator, I can add my numerators. Okay, so 2 over 3, our proportion there was 2 over 3 is 8 is to 12. I can subtract 3 here and subtract 12 there, and it would still be equal. They would still be equal, or I could add 3 and add 12. You add the denominator to the numerator. And just as you can have extended ratios, you can have extended proportions as well. So it doesn't have to just be 2 fractions. You can have more than 2 fractions. So an example would be like if I had 2 eggs to 3 cups of flour. That'd be equivalent as having 4 eggs to 6 cups of flour, or 6 eggs to 9 cups of flour. They still reduce to 2 over 3 eggs to cups.